the cylindrical coordinate system. Welcome back to Calculus 3. We're going to look at a different way to look at 3 dimensions. So to tee it up, you already know there are at least 2 ways to look at 2 dimensions. You looked at the rectangular coordinate system in 2D, like this, the X and Y axes. And then we learned the polar coordinate system. And the polar was just another way to look at 2D, right? Now, don't think that polar and rectangular are the only coordinate systems for 2D. There are other ones that mathematicians use, okay? But those are the only 2 we cover in this class. And the same for 3 dimensions. We're going to look at, we already looked at rectangular, we're going to look at cylindrical, and then next week we're going to look at spherical. And those are 3 different coordinate systems to look at 3D or deal with 3 dimensions. There's a lot more though. There's like hyperbolic and elliptical, and you could go look it up. It's good times. Go Google up all these other different coordinate systems. So cylindrical is really nice because I claim that it's going to be easy peasy for everybody, because if you understand polar coordinates pretty well, cylindrical is just an extension of polar. Really? Yeah, it's just an extension of polar to 3D. What do you mean? Well, a point P in space is represented by an ordered triple R theta Z. And the R theta is exactly the same R theta that you did in 2D, except for us, it's going to be the projection of your point down into the XY plane. So what do I mean? So if you had your point P here, when you project it down here into the XY plane, I'll call the shadow P prime, that's the projection. This point would have the first 2 coordinates R theta. And then Z is just the distance from the projection to the point. So Z is basically the same Z as itself. Okay, here's the conversion formulas that you need to go from rectangular to cylindrical. And the good news is some of it's review. Because check out the rectangular if you want to go from cylindrical to rectangular. X is R cos theta. You've seen that already when you studied polar. Yeah, it's the same. Y equals R sine theta. It's the same. And then here's even better news. Z is just himself. Z. No change. Easy peasy. And then these 2 should look familiar because you saw those when we were looking at the polar conversions. And then Z is just himself. Z. So let's convert some points. Then we'll look at a couple of converting equations. And then we'll actually do some triple integrals. So we'll take it easy. So let's just convert some points back and forth between the coordinate systems for fun, just converting points. So here is a point that's given to you in cylindrical. So that means that they're giving you the R and the theta and the Z in that order. So how do you get it to be rectangular? Well, X is R cos theta. So 4 cosine of 5 pi 6, I get 4 times negative square root of 3 halves, and that reduces to negative 2 square root of 3. Y is R sine theta, 4 sine of 5 pi 6. That's 4 times a half, which is 2. And Z is just Z, which is 3. So then put it all together. The ordered triple in rectangular coordinates would be that guy right there. There's your point, representing the same point in rectangular. Pretty easy. Next example, let's convert a point given to us in rectangular. So they're giving us the X, Y, Z, and we want to convert to cylindrical coordinates. Okay, R is the square root of X squared plus Y squared. So we'll have the square root of 1 squared plus square root of 3 squared. But that's just the square root of 1 plus 3. Ooh, square root of 4 is just 2. That was nice. Came out to a nice number. Theta is tan inverse of y over x. So tan inverse of square root of 3 over 1. Oh, heck, I don't have that memorized. Forget it. Go get the graphing calculator. And make sure you're in degrees mode when you do it, okay? Okay, so here in your graphing calculator, check your mode, and I'm in radians mode. You don't want to see the answer in radians. Go into degree, hit enter to make sure you choose it, and then get out by second quit. And then let's do a tan inverse of square root of 3. Yep. Whoops, too many of these. Parentheses. Oh, I guess I don't need parentheses for this one. Interesting. Okay. 60 degrees, and that is indeed pi thirds. Yay. Now you have to be careful because that might not be the right answer. What do you mean? Well, and we've studied this before, that this arctan has a limited range. The range is only for angles between negative pi halves and positive pi halves. Now this point here, when you draw it up and basically project it into the XY plane, it does exist here in quadrant 1, which is in the range of arctan. That does fall under the negative pi halves to positive pi halves. So this is okay. If it weren't, and we're going to see that in a moment, in the next example, you have to do something extra. Now Z is just itself, so that's just going to be a 2. So the final answer for example 9 is the ordered triple. So we converted to cylindrical coordinates, and it's going to be this ordered triple, the point 2, comma, pi thirds, comma, 2. Great. So let's convert another rectangular point to cylindrical. So here you're going to go, all right, well, r is the square root of x squared plus y squared again. Okay. And negative 1 squared is the same as positive 1 squared. So we're going to still get a 2. Nice. Now, theta is tan inverse of y over x, and tan inverse of negative square root of 3. Now, be careful. So if you do this on your calculator, I get negative 60 degrees, or negative pi thirds. That's wrong for this particular problem. What? Yeah, it's wrong. Well, what do you mean? So it says, negative 60 degrees, but that's wrong for this problem. It's not wrong in general. I mean, that could be an answer. But if you look at the projection of this ordered triple, negative 1 square root of 3 falls under quadrant 2. And I hope you could appreciate that this angle here is not negative pi thirds. So because we're over here in quadrant 2, rather, we have to add pi to this answer of negative pi thirds. So when we add pi, we get 2 pi thirds. And that is the correct angle for this particular point. Okay? And then Z is just Z, which is 2. So the final answer for example 10 is 2 comma 2 pi thirds 2. And that would be the correct cylindrical coordinates point. Okay, so be careful. Now let's look at converting equations now. We're done converting points. What about if you have an equation and you're trying to convert it from rectangular to cylindrical? You still use the conversion formulas. Here's some that are already converted for you, like x squared plus y squared equals 9, which is this cylinder. You would first do it slowly. You would replace x squared plus y squared with r squared. You'd get r squared equals 9, and then you would square root both sides. and you get r equals 3. That guy there, again, the x squared plus y squared, you replace it with r squared, and r squared equals 4z. You would square root both sides. And so here's a cone, and then here's a hyperboloid. So what are good candidates for converting this cylindrical? Why are we even learning this? Well, as before, when we learned the polar coordinate system, the reason why was certain double integrals were really tough to integrate if we were stubborn and wanted to stay in the rectangular coordinate system. Better to do the change of variables and convert when it makes sense. And for polar, it made sense when the region of integration was like a circle or a part of a circle or a polar sector. Similarly, in 3D, cylindrical coordinates is a good choice when your region of integration is a solid that looks like one of these guys. Okay? It's got symmetry about the z-axis. These are all solids that have symmetry around the z-axis. Cylinders, paraboloids, cones, and hyperboloids. Those are good candidates for converting the cylindrical coordinates. So let's convert a couple of equations. So here's an equation in rectangular, y squared equals x. How would you convert that to cylindrical? By brute force, you replace y with r sine theta and x with r cos theta. Those are the conversion formulas. You're almost done. They usually like you to solve it for r. Even though this is true, the typical trick is to do something that's usually illegal in math, divide by a variable, but we'll assume that r is not 0, so we can divide it by 0. And then finally, solve for r. That's standard. And so your answer is cos theta divided by sine squared. Sometimes they may want you to go an extra step. So sometimes when you'll notice in the back of the book, this might not actually be the answer that's shown in the back of the book. And you're like, hey, am I getting it wrong? They may use a trig identity or two. So they rewrote cos over sine squared and then use some trig identities that cosine over sine is cotangent and 1 divided by sine is cosecant. So an answer here is r is the product of cotangent theta cosecant theta. I love this one. I always give this one to my trig students when we do polar. X squared plus y squared gets replaced with r squared. Y gets replaced with r sine. And then the trick is divide both sides by r, assume r isn't 0. You do pick up r equals 0 anyways in your final answer, so you're okay to do it. Final answer, r is 2 sine theta. This one is kind of tricky because this is a theta equals something instead of r being a function of theta. So this one, you usually won't see that in our module, but it's kind of fun. It is something that could get converted to rectangular. How the heck would we do it? We use the fact that tan theta is equal to y over x. Really? Well, what do you mean? You take tangent of both sides of this equation, like this, and then tan theta gets replaced with y over x, like that. Kind of tricky, huh? And then what the heck is tan of pi 6? I don't know, but let's rewrite it using a trig identity. Tangent is sine over cos, and then we can figure out what sine of pi 6 is. I think that's a half, and then cosine of pi 6 is square root of 3/2. And this looks yucky when you're dividing a fraction by a fraction. So let's turn it into a multiply by the reciprocal. And then we'll get y equals 1 over square root of 3x. And this is a plane. Let's do the reverse. Let's take something in cylindrical and convert to rectangular. This is a tricky problem because the trick is doing something that's typically illegal in math, and that is multiply both sides by a variable. That's dangerous because you could be multiplying both sides of the equation by 0, which is not legal, but we'll assume that r isn't 0. Then you use your conversion formulas. R squared gets replaced with x squared plus y squared, and r cos is the same as x, and you're done. And this is a circle if you are in 2D, and it's a cylindrical surface if you're in 3D, okay? All right, quickly now, here's some set notation describing some regions in 3D, and you know, here r is going between 0 and 3, theta is going between pi 0 and pi thirds, and z is going between 1 and 4, and that's like a thick pizza slice, And the answers I put below here. So there's a picture of letter A. There's the answer for letter B here. It's an upside down cone. And this last guy showed you a nice picture. It's a cylindrical shell. It's a shell with the core cut out of it. It's hollow there in the middle. Pretty cool. All three of these solids are good candidates for converting the cylindrical coordinates. They're all three good candidates. Okay, enough about that. Let's get to it. Let's get to business. Well, what's business? How do you get a triple integral and convert it to cylindrical and then do it? Okay, we'll do a couple. Now, folks, you're going to notice in my lecture notes, I only do a few examples of triple integrals and cylindrical coordinates, as opposed to next week when we get a spherical, I do a lot of examples. So you may be going, well, are you giving cylindrical coordinates the short shrift? You know, cylindrical, are they getting, is cylindrical getting gypped? No, not at all. The reason why I don't spend as much time is because cylindrical is easy for most students because it's just sort of polar with the z-axis sort of hacked on, you know, jacked on to the polar coordinate system. And since most people already got a lot of acquaintance with polar, dealing with polar with the z-axis just jacked on, it's not really too hard. So I do a few examples and that's usually enough. Okay, so how would you iterate a triple integral in cylindrical? Well, you've got a solid and the projection of your solid R onto the XY plane can be described in polar. See, and you already know about polar, so that's good. And let's say your Z limits go between some underbelly up to some capping surface. Then when you're trying to do a triple integral and you're integrating F, that would be maybe some density function here if you were trying to find the mass of your solid, you would have your Z go from some low limit to an upper limit. And then you'll notice that the limits for R drd theta, and yeah, you're still going to need your R in here because your volume element, your dV, is dz r drd theta here in the cylindrical coordinate system. This is the volume element. Okay, all right, so let's do an example. Okay, look at this mess. They're telling us cylindrical coordinates and you want to, like you don't even want to try to do this in rectangular because it would end up being a trig sub kind of problem. Yuck, not fun. But just looking at it, it's like, really? Okay. All right, so let's convert everything to cylindrical. First up, what I do is I always sketch the region in the XY plane, even if they don't ask me to. Do it anyways, because otherwise you may get into some issues and you'll pick wrong. So x equals -3, x equals +3. Okay, those are vertical lines. Graph those. 1, 2, 3, 1, 2, 3. And then y equals -√9 minus x squared. What does that graph look like? That's the lower semicircle of a circle centered at the origin of radius 3. And then y equals +√9 minus x squared is the upper semicircle of a circle centered at the origin of radius 3. So this is the base, and that's our region in the XY plane. Great. So let's talk about what r and theta are doing here. R looks like it's going between 0 and 3. Theta looks like it's sweeping out a full revolution, 0 to 2 pi. Wonderful. So when we do this, you're going to go like that. Your volume element, you replace the dz with dz r dr d theta. Y squared is the integrand. So y is r sine theta, and you're going to square it. Now, so you got your theta going between 0 and 2 pi, r is going between 0 and 3. What the heck are the limits for z? Look at what the limits are for z here. Remember, z is z. And so the lower limit, we have z equals 0, so that won't change. The upper limit is 9 minus x squared minus y squared, but that's no good. You don't want to see x's and y's in a triple integral with cylindrical. Well, how come? Because x and y are variables that we reserve for rectangular. Well, then what the heck? Well, if you factor out the negative from the x squared and y squared terms, you can hopefully see how you'll convert this to what?
R squared.
Yeah, very good. So 9 minus r squared is our upper limit for z. Okay, great. Let's make this happen. So r sine theta squared is really r squared sine squared. Okay. And then this r, I don't want to forget him because I might accidentally erase him. Let's multiply him with the r squared so we get a single power of r. And then we can integrate. That way we won't forget about the r. Okay. I'm going to integrate with respect to z first, which means r and theta are held constant. So I'm just going to copy down the r cubed sine squared theta, and then I'll just have z, and z goes between 0 and 9 minus r squared. And that's just going to end up being 9 minus r squared. Now what? Yeah. Well, you have to integrate with respect to r next, but you don't want to have all your r's hanging out everywhere. And don't distribute the sine squared theta. I know you could distribute this entire product, but why do that to yourself? It's going to be messy. Don't do it. It's harder to read. So what I'm trying to say is distribute the r cubed only, since the sine squared theta is just a multiple, and you're not even going to integrate with respect to theta till the very end. So only distribute the r cubed. Okay. Then what is r cubed times r squared? Quick, because a lot of students blow this and then they blow the whole problem. Is it equal to r to the 6th, or is it equal to r to the 5th?
R to the 5th.
Very good. Yeah. So now let's integrate with respect to r. So the sine squared theta is just a multiple. It just goes along for the ride. And the antiderivative of 9r cubed minus r to the 5th is 9/4 r to the 4th minus r to the 6 over 6. And that's going to get evaluated between 0 and 3. So when I evaluate that number, it's not pretty, people. I get 243/4. Okay, let's just bring it out in front. Now what? Power reduction formula. Sine squared requires the power reduction formula to integrate. You remember, you're Calc 2 folks. So what's the power reduction formula for sine squared? It's, 1 minus cos 2 theta all over 2. So I don't like fractions. So before I even start, so I don't forget, I bring the half out. And so 1/2 times 1/4 is 1/8. And then I just worry about integrating 1 minus cos 2 theta. And for this guy, when you use u sub, he's going to need a 1/2 in there. Not the whole thing. Don't put a 1/2 here and then multiply this whole integral by 2. That would be bad. You're really integrating the 1 all by itself, which is just theta. And then when you integrate the cos 2 theta, you end up with the 1/2. And then that antiderivative will be sine of 2 theta. And then we're evaluating between 0 and 2 pi. It turns out when you evaluate the sine of 2 theta at either 2 pi or 0, he doesn't contribute anything because sine of 4 pi is 0 and sine of 0 is 0. So he's no fun. He doesn't contribute anything in this particular problem's answer. Only the theta does when you have him be a 2 pi. And I'll reduce this to lowest terms and I'll get 243/4 pi. And that's the final answer to the triple integral. Woo! And that concludes that example. So there is your first converting to cylindrical coordinates triple integral. Not too hard, right? We did have to end up using the power reduction formula. I'm really a power reduction formula person, and so on this coming Sunday's quiz, there will be a problem on there that will require a power reduction formula. Just know that. So it's going to be one of them. Okay? Oh, yeah. Gotta know it. Okay, what about, and not because you're doing cylindrical on this week's quiz. Cylindrical is not going to be on this week's quiz. Well, wait a minute. You just said I'm going to do power reduction formula. Yeah, but it's going to be for one of the polar coordinates problems. Because remember, it came up for polar coordinates also, needing that power reduction formula. So be aware. Okay, here's something that I stole off of MyLab Math. That's right. This is a MyLab Math problem. So what it is they have a bunch of blanks where you have to type in what those blanks are. You know, you've done this in MyLab Math, right? Type in, fill in the blank. So they want you to set up a triple integral in cylindrical coordinates that would find the volume of the solid in the first octant. Okay, that's good to know. That's always key if they do say that. Bounded by the cylinder, x squared plus y squared equals 25. So that's a circle centered at the origin of radius 5, but we're only going to consider the first quadrant since they said the first octant. And the plane z equals x, and this is the capping surface. So this right here is the base of the solid. And that lends itself very nicely to polar, so we can immediately figure out the limits for r and theta. So this one looks like r will go between 0 and 5, and theta is 0 to pi halves. Okay. Remember, polar and cylindrical are very closely related. So they already have dz r d theta there for us. So what's missing? Like what goes here in the integrand? Does anybody know?
Just one.
You're close.
Or
R. Now they tried to trick you here. They went, oh, we've got the volume element. Yeah, but cylindrical needs the R. Remember, you got to be a pirate. Be a pirate. You need that R. R. Yeah. Okay, now what? Well, the d theta, we got him already. We got the 0 to pi halves. So we got that outermost integral limits. Yay. And then the middle integral, we already got his limits, 0 to 5. Now, what are we going to do for the z limits? Uh-oh. Well, we know that the base of the solid is in the xy plane, which has the equation z equals 0. So that'll be the lower limit for z. And then the capping surface gives you the upper limit, but you're not allowed to put an X here. Well, why not? Because, you know, this is cylindrical coordinates. You're not allowed to have X's, Y's, or Z's. So what should we put here instead of X?
R cosine.
Very good. R cos theta. Perfect. And we're done. And then you can easily evaluate this integral. This integral is super easy to evaluate, so let's just do it. So first, we're going to integrate with respect to z. And the r is just a multiple, so we'll have rz, where z goes between 0 and r cos. Not too hard. Used to say cos. Man, my handwriting just gets worse and worse. Sorry. And then before you integrate with respect to r, make sure you multiply all of your powers of r together. And don't, you know, put the cosine theta over to the side. It doesn't interfere. It's just a multiple. And then the antiderivative of cos theta r squared is cos theta r cubed. And r is going to go between 0 and 5. I think 5 cubed is 125. So I'm just going to pull the 125 thirds out in front. And then I'm going to integrate cosine theta with respect to theta. And that's positive sign, not negative sign. Only when you take the derivative of cos do you get a negative sign. And then our final answer is what? What the heck is sine of pi halves? I think it's a nice number, right? Final answer, 125 thirds cubic units. And there's your volume of that solid. Cool. All right, one more problem and then we're done for the day. Yay. One more, cylindrical coordinates. We're going to do a mass problem. Oh, we got to do mass. Got to find mass of a solid. So mass of a solid is equal to the triple integral over the region. Here's the region. They're calling it big D. And then the density function is what you put here for your integral when you're finding mass. And this is going to be over D and some volume element. Yeah, okay. And they're telling us convert to cylindrical. And why should we? Well, it turns out that this solid they're giving us is, if you looked at what's going on in the XY plane, and I would, even though they're not telling you, like, go do it. X is going from 0 to this weird number, 2 square root of 2. And then Y is going from negative square root of 8 minus X squared. And that's the bottom half of a circle centered at the origin with radius 2 square root of 2. Because square root of 8 is 2 square root of 2. And all the way to the upper semicircle, that's the graph of positive square root of 8 minus X squared. Now, is it the whole circle? Be careful. No. Remember, X is going from here to here. So your region is this right here. This is the base of your solid. It's the half of a circle, a semicircle, the right half of a semicircle. And Z is just going from Z equals -1 to Z equals 2. If you graphed Z equals -1, that's just a plane that intersects the Z axis at -1. And then Z equals 2 is just a horizontal plane at intersecting the Z axis at 2. So the top and the bottom are just planes of this solid, okay? And we've got a variable density. Okay, so if I were to iterate a triple integral that is going to represent the mass for this guy, yeah. Okay, I'm going to convert square root of X squared plus Y squared plus 1 to cylindrical. That's just going to be square root of R squared plus 1. The volume element is going to be R dz dr d theta. Okay, Z is a pure number to a pure number, -1 to 2. They told us that. So R is going from what to what here on this semicircle? 0 to 2 square root of 2. Theta is going from negative pi halves to positive pi halves. So that's the hard part, is setting it up. So now integrate this with respect to z. So that's just a constant. And z is going to go between -1 to +2. So 2 minus a -1 is equal to 3. And I'm just going to pull that out in front. This is a 1. And you know we're going to use the power rule with u sub right now. So tell me the u, and then tell me the du. I need a 2. This is how I roll. I like to put a 2 in, divide it out. So this integral right now looks like square root of u du. Radicals are evil. Rewrite it as exponents. Antiderivative is 2/3 u to the 3/2. Back substitute for u. Back substitute your r squared plus 1. So now what do you have? You got 3/2. Yeah. 2/3. I'm going to pull the 2/3 out. And you've got r squared plus 1 to the 3/2. And you're evaluating that between 0 and 2 square root of 2. Yuck. That looks terrible. Yeah, I know. 2 square root of 2 squared plus 1 to the 3/2 minus 0 squared plus 1 to the 3/2. Woo! Yuck. Remember, this is just 8. So 8 plus 1 to the 3/2 is actually a nice number because that's square root of 9 cubed. Yeah. In other words, that's just 3 cubed, which is 27. And this here is just a 1. So your integral just ends up being nice. 27 minus 1. Ah, that's just 26. And then when you integrate with respect to theta, oops, got my limits are not 0. Negative pi halves, positive pi halves. So your final answer is your mass is 26 pi. Don't put units on here because mass is unitless, just 26 pi. And that concludes the cylindrical coordinates. So congratulations. You now know what that looks like. And that concludes today's lecture.